going to try to pronounce this name. My Fanny? She's not here. Okay. Daniel? Hi, Daniel. In the last lecture, I talked about how when the electrons in a typical metal is excited, we estimate that the total energy is proportional to T squared. So there are actually two factors of T, right, in the T squared. So each of them comes about because of a different reason. Do you remember what one of the reasons might be?
No.
Sorry?
No, I got really drunk this weekend. I've got like no memory.
Good, so you had a good weekend then. Does anyone remember, or could anyone tell me how the T's in the energy come about?
One due to the vibrational energy.
Oh, no, the electrons.
Yes.
The electrons, not the vibrations of the atoms. Right. Just the electrons part. Okay. Well, there are two factors of T. So it's one of the factors come about because as I described, in a typical metal, most of the electrons are stacked up in the energy levels from bottom up. And at room temperature, only those that are at the highest, that are close to the Fermi level, would get excited. Right? And from the equation of the Fermi direct distribution, we can estimate that those at the very top would get excited by an amount which is roughly equal to kT. Okay, the very sharp step in the distribution becomes slightly smoother, and we can estimate that the width of that smoothened bit is about kT. So that's one factor, right? The other factor is that those that are excited, they are excited in above the Fermi level, where there are a lot more energy states for them to occupy. Unlike those at the bottom, which have to be stacked up and they are stuck there. Right? So those at the very top, they can behave like ideal gas. Right? They would be in a situation where they have lots of energy states and lots of room, but comparatively fewer electrons. So it becomes unlikely, or a lot less likely, for any two of them to want to occupy the same state. Right? Not that they are allowed to by the exclusion principle, but I mean they would not be likely to in any case. And because of that, they behave like an ideal gas. And we have learned earlier on that for an ideal gas, the energy of an atom in the ideal gas would be about 2/3 of kT. All right, so that gives us the other factor of T. Okay, so that's how we get the two factors of T in the energy. And from this, we can differentiate it to get the heat capacity. Okay, and when you do it a bit more accurately, using the density of states to actually calculate how many available states that you would have just above the energy level within this energy range of kT, you will get that formula that you see right at the top of the slide. So we actually have a formula now that can allow us to estimate the heat capacity in an electron. And notice that it depends on t to the power of 1. It's linear, it's proportional in t. Which means that if you plot the graph with respect to t, you should get a straight line. But in order to verify this experimentally, there is this complication, right? That at the low temperatures that we normally need to measure it, there are also contributions from the lattice vibration. Okay, so that's where the vibration part comes in. Okay, because when we measure the temperatures, the electrons would take up heat energy when we heat up the metal, but the same heat energy would also cause the atoms to vibrate. So both of these will contribute to the heat capacity. And the trouble is well, in fact it's not a trouble, it's a good thing in this case. The thing is that, as we will see in the subsequent lectures, the contribution from the vibration at low temperatures is actually proportional to T cubed. Instead, unlike the electrons, whose heat capacity is proportional to T. So they are proportional to different powers of T, and this actually gives us a way to resolve the two, to pick out the two of them separately. And the way to do it is, when we measure it and plot the graph that we need to rearrange the equation in the form that you see at the bottom of the slide. Okay, the T and T cubed takes the form at the bottom, and when you plot the graph, well, when physicists did the experiments and plot the graph, they found that it is indeed a straight line. So that single graph actually proves two things. Right? At the same time, the graph that you see there, it shows that the electron heat capacity is proportional to T. It also shows that the heat capacity due to the lattice vibration, the vibration of atoms, is proportional to T cubed. But for now, we are more interested in the electron part. And I've also mentioned that the vertical intercept of the graph gives you the gamma factor. Okay, so just very quickly, if you look back at the equation at the bottom there, you see that the gamma in that equation gives the vertical intercept if you plot a straight line. Now this gamma is of interest, in fact it's quite important, because according to this equation that we derive, the gamma here is the part in the equation that is constant with respect to the T. So let me take out the gamma. Right? The T is there, that's the T and that's the T. The rest of this is the gamma. Okay? That's the gamma. So that means that if the theory is perfectly correct, we should be able to calculate this gamma from here. It's just pi, that's the number of electrons, Boltzmann's constant, Fermi temperature. Let's see what the Fermi temperature depends on. Fermi temperature depends on the Fermi energy. That's how it's defined. Okay, and the Fermi energy, in turn, looks like this. That's what the Fermi energy look like. So that's Planck's constant, n over v, the number of density, m, the mass of the electrons. So these are numbers that we can find, that are usually known. So in principle, if you put in all these numbers, we should be able to find gamma. Okay, and then compare it with the vertical intercept. And they should agree if the theory is perfectly correct. But they don't. They usually don't agree. So what we have